Okay, 4.4, the rational root theorem. Let a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus, and that pattern continues all the way down to a sub 2 x squared plus a sub 1 times x plus a sub 0 equals 0. Represent a polynomial equation of degree n with integral coefficients. If a rational number, p over q, is a root of the equation, then p is a factor of a sub 0 and q is a factor of a sub n. Basically what that's saying is that if you look at the last number, a sub 0, and the first number, a sub n. Because a sub n, all the way down to a sub 0, simply just represent the coefficients, the numbers that are in front of the variables. A rational number, p over q. Okay? P over q is a root if p is a factor of a sub 0. So the top p is factors of the last number, a sub 0. And q is a factor of a sub n. So the bottom of the fraction is factors of the first number, a sub n, as you can see. First and last. So that's all we're going to do. It's going to make a lot more sense once we get into this example here. So let's take a look at the example. List the possible rational roots of the equation 6x cubed plus 11x squared minus 3x minus 2 equals 0. Then determine the rational roots. Okay, possible rational roots. That's going to be p over q. P would be the factors of the last number, in this case, 2. You could also say negative 2. Really doesn't matter because when you look at the factors of 2 and negative 2, they are the same. Q, factors of the first number, 6. So if we look at the factors of 2, it's going to be plus or minus 1 and plus or minus 2. If you wish to write them out as 1, negative 1, 2, negative 2, that's fine as well. You'll see that this will get very lengthy here if you do that, though. 6 plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. So we have 2 numbers on top being divided by 4 numbers on the bottom. We must consider all of those possibilities as possible roots. So let's divide them out. 1 divided by all of those numbers, 1 divided by 1 is 1, 1 divided by 2 is a half, 1 divided by 3 is a third, and 1 divided by 6 is a sixth. And then we take 2 divided by all those numbers. 2 divided by 1 is 2. 2 divided by 2 is 1. We have already written that down, so we're not going to write it twice. 2 divided by 3, that's new, 2/3. And 2 divided by 6 is 1/3. We already have that written down. So this is all of the possible roots. There are 2, 4, 6, 8, 10, 12 possibilities. Now we know from previous sections that the most roots that we could have is the degree of the polynomial. As you can see up here, the degree is 3. So we should only have 3 roots for this equation. They could be all real. We might have some imaginaries in there. 3 is the most we can have. So there's 12 here possible roots. 12 possible roots, only 3 at the most could work. So there's going to be a lot that do not work. So how do we find the ones that work? Well, I'm suggesting that you use synthetic division. So let's set up our synthetic grid. 6, 11, -3, and -2. Again, those are the coefficients from our formula up here. And we just try all the possibilities. We may go through all 12 of these and find that none of them work. Okay? There is a way to do this with the graphing calculator to know which roots work. Okay? There is a way to do that. But at this point in time, you get to the higher level maths, you get into college, you're going to find that the calculator is going to be used less and less and less to the point where they might not allow you to use it at all. So we need to start figuring out things without the calculator. So we can run through some of these. Let's start out with, say, 1, 6, 17, and we get a remainder of 12. You get a remainder of 12, that is not a root. So 1 doesn't work. You can X it out. You can erase it. Either way, we have no use for it. So we're just going to erase it and start over again. Like I said, we could do this 12 times. Let's try -1. -6, 5, -5, -8, 8, 6. That doesn't work either. Again, we're looking for a remainder of 0. Okay, we've done 1 and -1. I'm going to go ahead and jump over to 2 and -2. I'm going to go ahead and just go straight to -2. So -12, -1, 2, -1, 2, 0. -2 works. So that means we have a root. X equals -2. We also now know a factor. X plus 2. Every root gives us a factor. We find that by setting the root equal to 0. Get it equal to 0. Get rid of any fractions if we have any. Okay? Get it equal to 0, and we have the factor. Now, what we have left over is a quotient. In this case, it's a quadratic. What I want you to do with these problems is, no matter what the power is, I want you to try to break it down to at least a quadratic. Because you, right now, know how to solve quadratics, either using factoring, completing the square, or quadratic formula. We can get the rest of the roots by solving this quadratic formula. So the quotient tells us that quadratic. We'll now solve it. And this actually does look factorable to me. So we need a -1. Looks like we'll go 3 and 2. 3x, 2x, 1, 1. I need a -1 in the middle, so I'm going to put a -1 plus 1. How do we check that? Outside and the inside. The outside gives us a -3x. The inside gives us a positive 2x. If we put those two together, -3x plus 2x gives us a -x. That matches our middle term. That's how you check a FOIL. So this works. Now we'll set each factor equal to 0 and solve. So 3x equals -1, x equals -1/3. 2x equals 1, x equals 1/2. So those are our other two roots. X equals -1/3 and x equals positive 1/2. The factors that gave us those are right here. 3x plus 1 and 2x minus 1. So you can see that if we have a fraction, you would move it over and get rid of it. So if we did move that over, just to show you here, if x equals 1/2, we'd say x minus 1/2 equals 0. So if you said equals 0, that would be your factor. And then multiply by 2 to get rid of the fraction. And that's where we get that factor. Okay. Just in case say you tried a fraction first instead of an integer, and you get the fraction to work synthetically up here where negative 2 worked, you wouldn't have the work to, or you wouldn't have the factor from factoring to know what that factor was. So you're going to have to work backwards to figure out what that factor is. So we have the roots. We have the factors. Okay. What I'd like for you to do with the factors is I'd like you to rewrite the original polynomial, which in this case is (6x cubed plus 11x squared minus 3x minus 2). I want you to write it in factored form. So that's x plus 2 times 3x plus 1 times 2x minus 1. So I want you to get the roots, and I want you to write the polynomial in factored form. We're going to do this 2 more times. This is all we're going to do with this section. So here's another example. Find the roots of x cubed plus 8x squared plus 16x plus 5 equals 0. We must first look at the possible roots. P over Q. P is the factors of the last number. Q factors of the first number. Plus or minus 1, plus or minus 5, plus or minus 1. Some people ask me, why don't we, instead of using P over Q, use L over F, last and first? Actually, I don't see why we can't. That probably makes a lot more sense. Last and first when you're dealing with polynomials. Factors of the last, factors of the first. Not sure why we've never used L and F. Someone did ask me that. I don't have a problem with that. If you want to write L and F instead of P and Q, that's fine. I'm going to stick with P and Q. Possible roots. So 1 divided by 1, well, both of those divided by 1 are going to be plus or minus 1, plus or minus 5. So we have 4 possibilities here. 3 is the most that we're going to get. So we have to see which one's going to work. Again, it takes time to do this. If you don't have a calculator, it's going to take a lot of time. Let's go ahead and right now take a second to show you how you can check which of the possibilities are going to work. Okay, we're going to look at a graphing calculator, and we're going to do that by going to y equals and graphing the original function. So x to the third plus 8x squared plus 16x plus 5. And I'm going to set y2 equal to 0. 2 reasons. 1, the polynomial is equal to 0. That's how you find the roots. 2, in order to use a way to calculate the intersection, to calculate the roots, I'm going to use the intersection. Let's first go to the graph. It's a nice cubic. We can see it's crossing 3 times. Looks like to me it's crossing at -5. This one in the middle, not so easy to see, and this one's not so easy to see. So let's go ahead and calculate. Second trace. Now, this is where I was talking about the intersection. In order to find a root or an x-intercept or a 0, we could use the 0 function, number 2. But the 0 function requires a left and a right, and I found more people get confused with that, so we're going to try to simplify the process by using number 5, intersection. So choose number 5, and then it asks for curves. It's going to ask you for a first curve, a second curve, and a guess. Here's why this is simple. All you have to do is move the x close to where you think there's going to be an x-intercept. You hit enter 3 times, and it finds it for you. You don't have to worry about left, right, anything with that. Enter, 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 and it says -5 works. So I'm going to use -5 over here. So let's go ahead and put -5 in. -5, 3, -15, 1, -5, 0. And it did. It worked. Okay, so we have root x equals -5, which gives us the factor of x plus 5. Okay, back to the graph. Calculate number 5, the intersection. We're going to move it over to the next one and enter 3 times. And it's saying -2.618. -2.618. Well, the only possibilities that we have is plus or minus 1 and plus or minus 5. So that is not one of our possibilities. And if we calculate the last one, -0.382. Again, not one of our possible roots. It's not nice. If you get not nice decimals like this, you're probably going to end up with square roots in your solutions. So the graphing calculator helped us slim it down to -5. And if you have a lot to try, this is a great way to speed up the process. Okay? If you don't have a calculator, though, you can still figure out which one works by just plugging them in until you get a 0. What's left? Our quotient is going to help us solve for those decimals. X squared plus 3x plus 1 equals 0. Okay, that is going to give us those other ones. This is not factorable. There's no way I can put 1 and 1 together to make 3. So we're going to have to use either completing the square or quadratic formula. I personally like completing the square, so we're going to use that method. X squared plus 3x. We're going to move the number over and replace it with a quantity squared. What goes in a quantity squared is half of this number right here in front of x. So half of 3 is 3/2. So we get x squared plus 3x plus 9/4. And on this side, we'll get -1 plus 9/4. Now the left side is a perfect square. It factors to x plus 3/2 and x plus 3/2. And that's the way it's set up to be. It will always factor to the square root of this number right here. Square root of 9/4. Well, the square root of 9 is 3 and the square root of 4 is 2. It will always factor to that. Always. That's why we did that. The right side, 9/4 minus 1, that's going to be 5/4. So we can write the left side as a quantity squared equal to 5/4. And we can now solve that by square rooting both sides. So x plus 3/2 equals plus or minus the square root of 5/4. Getting x by itself, we'll subtract the 3/2 and then take the square root of the top over the square root of the bottom, which gives us our solutions. We have 2 of them. X equals -3/2 plus the square root of 5/2, and x equals -3/2 minus the square root of 5/2. I'd like to get the equivalent decimals on that so we can match it up to see how the graph worked out. See if we get the same decimals here. So -3/2 plus the square root of 5 divided by 2. And you just recall that and go back and change it to a minus. Get the second. So -0.382 and -2.618. So those are our roots. We got the decimals from the graph as well earlier. Those match up to the graph. When we're writing down the roots, I want the exact answers. So if we scroll back up here, it's going to be 3/2 plus or minus the square root of 5 over 2. So x equals negative 3/2 plus the square root of 5 over 2. And x equals negative 3/2 minus the square root of 5 over 2. Now, what are we going to put down for its factor? Well, when you get square roots, I want you to stop at whatever quadratic you solved to get that. So we're going to say that the factor for these two is this original quadratic quotient that we got. Again, in a previous lesson, I told you when we get a remainder of 0, we know two things. We know that what we divided by is a factor, and we know that the quotient is also a factor. So x squared plus 3x plus 1 is also a factor of that. We're not going to break it down. We could. We could say x plus 3/2 minus the square root of 5 over 2, but it really doesn't help us. There's really no use to doing that. So we have our roots. And now we're going to write the original cubic in its factored form. So x cubed plus 8x squared plus 16x plus 5 equals, not equals 0, plus 5 equals x plus 5 times the quadratic x squared plus 3x plus 1. So there's the cubic in its factored form. We have the roots. Again, the calculator does make it faster. You do not need it though. Okay, the higher level maths will require you to figure these out without the use of a graphing calculator. All right, let's do the last one now. Find the roots of 2x to the 5th plus 3x to the 4th minus 6x cubed plus 6x squared minus 8x plus 3 equals 0. Wow, that is a very large polynomial. X to the 5th, we've not dealt with that before. Let's see what we can do here. Let's at least start by looking at the possible roots. Again, P over Q. Those of you that like the L over F, last over first, factors of the last. So that's the factors of 3, factors of 2. So plus or minus 1, plus or minus 3, plus or minus 1, plus or minus 2. So we're going to divide this out to get all the possible roots. 1 over 1 is 1. 1 over 2 is a half. 3 over 1 is 3. 3 over 2 is 3/2. Again, to speed up the process, unless we just try every single one, we can look at the graph. Okay, x to the 5th, 2x to the 5th, plus 3x to the 4th, minus 6x to the 3rd, plus 6x squared, minus 8x plus 3. And y2 we have set equal to 0. Let's go ahead and start with a zoom 6. Okay, if we want to see what this looks like, we can change the window. But just by looking at what we have right here, looks like -3 is a good chance, just by looking at the graph. and looks like positive 1. So negative 3 and positive 1 looks very good here. If we did change the window so that we could see this graph, we're going to change the y, min, and max to negative 100 and 100. Okay, it's a nice looking graph. Nothing special. Really can't see what's going on near the origin now that we zoomed out. But negative 3 is still looking good. And I said if we go back to the zoom 6, positive 1 looks like a good possibility. So let's try those out. 2, 3, negative 6, 6, negative 8, 3. So negative 3. Okay, it worked. So we got a root. And we have a factor. And also we said positive 1 looked pretty good. So let's see what positive 1 looks like. Now again, when we do this, we're going to break this down. We're only going to use the quotient, okay, when we're breaking this down synthetically. 2, negative 1, negative 1, 2, 2, negative 1, negative 1, 0. Good. Works out. Okay, those two look good. Those were just guesses. Let's go back to the graph. I'm going to go ahead and zoom in, zoom 2. Zoom in near the origin so I can see that third one. The third one's right here. Looks like to me about a half. We have a half as a possibility, so let's try that. The reason why I'd like to go further is because we've only broken this down twice, which means we've broken it down to a cubic. Now we can handle some cubics. We have done some grouping. We haven't done that much with factoring cubics, so I feel much more comfortable if we could break it down to a quadratic. So let's try a half, see if it works. If it doesn't work, we'll deal with the cubic. It does work. Excellent. So x equals a half. Now when we get the factor on that, there's a good example. If we move the fraction over, and then multiply by 2, that's where we get that factor. So we end up with 2x minus 1 as our factor. All right, let's see what quadratic we have left over to deal with. We have 2x squared, no, x plus 2 equals 0. Okay, fantastic. First thing that I would do with this quadratic is definitely GCF. Okay, greatest common factor. We can factor out a 2. When we're solving this equal to 0, the 2 is pretty much not going to help us at all. So x squared plus 1 equals 0. We can go ahead and get rid of that x squared. I'm sorry, get rid of that 2 and just make it x squared plus 1. Okay, so this is what we want to deal with right here, x squared plus 1. You have a GCF, you want to factor that out. Okay? Solving this, x squared equals negative 1. X equals plus or minus the square root of negative 1. Now we defined that earlier in a previous lesson. The square root of negative 1 is I. So we get x equals I and x equals negative I for our other two roots. Those are imaginary roots. And also from a previous lesson, if you remember, when looking at the graph, if there are 3 real, there's a total of 5 possible roots, the other 2 must be imaginary roots. Because remember, the degree tells us a number of total complex roots. Those could be real, those could be imaginary. Since we only have 3 real ones, the other 2 must be imaginary, and we just found them. x equals I, and x equals negative I. Now again, when we're writing this, we have imaginaries, or if we have square roots, I want you to write it in its quadratic form. So we go back up here. Now, do we use this or this? Do we use 2x squared plus 2, or do we use x squared plus 1? The answer is we use the x squared plus 1. You always use the reduced form. The GCF does not have any effect on that factor, so we're going to use x squared plus 1. You can pull a GCF out, do it. Get rid of it. Use the reduced factor, x squared plus 1 as your factor. Plus, if we did multiply this back out, we took this over, we got x minus I equals 0, we got x plus I equals 0, and we work this actually out, we would get x squared plus 1. That 2 would not be there because it's not part of that. So, 5 roots. Rewriting the x to the 5th. I need to use my notes to write that one down. Okay. 2x to the 5th plus 3x to the 4th minus 6x cubed plus 6x squared minus 8x plus 3 is equal to x plus 3 times x minus 1 times 2x minus 1 times x squared plus 1. That is a x to the 5th factor. That's pretty awesome. You could factor an x to the 5th. So that's it. That's the 3 examples I have for this lesson. Lesson 4.4, the rational root theorem.